A vector can be represented by line segments. The length of the line will be the magnitude of the vector, while the direction of the line, the way in which it's going, gives the direction of the vector. So in this example, we have a line PQ. So this direction from P to Q is the direction of this vector A. If the vector is represented in Cartesian coordinates with the initial end at the origin, in this case P is the origin here. We write it as O since it's the origin. With the initial end at the origin, the coordinates of Q represent the vector. So these coordinates, the x coordinates is A1, the y coordinates is A2, and the z coordinates is A3. These three coordinates are enough to describe our vector. So this vector A is equal to A1, A2, A3. Vector A can also be written in this way, from the, just as we did here, from the initial end of the vector to the end. This case is OK, this one PQ. Now the magnitude of the vector is written using the symbol for absolute. Written like this. Modulus of the vector is the length of the line segment. So this is the formula for it. We have square root of A1 squared plus A2 squared plus A3 squared. If it was a two coordinate system, just x and y, this A3 will not be here. That would be square root of A1 squared plus A2 squared. I think most of us should be more familiar with that one. But in a 3-coordinate system, the third coordinate is added also. So we have square root of A1 squared plus A2 squared plus A3 squared. And the direction of A, remember that A is a vector. We cannot talk about magnitude alone. We also have to talk about the direction. Direction of A is given by the direction cosines. These direction cosines are the cosine of the angle that the vector makes with each coordinate. So the angle that it makes with the x coordinate, if this is our vector A, the angle that it makes with the x coordinates is A1. That is this angle here. The angle that it makes with the y coordinates is A2. And the angle it makes with z coordinates is A3. Now the cosine of A1 will be the x components over the magnitude of the vector, which is A1 over this square root of A1 squared plus A2 squared plus A3 squared. Same goes for alpha 2 and alpha 3. Cosine of alpha 2 is A2 over square root of A1 squared plus A2 squared plus A3 squared. Cosine of alpha 3 is A3 over square root of A1 squared plus A2 squared plus A3 squared. So when we know these three direction cosines, it allows us to get the direction of the vector because we know the angle it makes with each coordinate. So we'll move on to vector algebra. Here we are going to be considering addition, subtraction, and multiplication of vectors and scalars. So to add two vectors together, we simply add those coordinates. The x coordinate of A, x coordinate of B, we add them. Y coordinates, we add them. Z coordinates, we add them. Looking at it from the perspective of the line segment representation, we can see that this is A. This is vector A, OP. This is vector B, OK. Now, if we want to add them, it's just like the parallelogram law of vectors that we may have seen in physics. The end of vector A we placed at the beginning of vector A, vector B rather, we placed at the end of vector A. So this vector will be shifted up to here. And then the final end of vector B from the beginning of vector A to the final end of vector B, be our resultant vector, that is A plus B. So to add these two vectors A and B, we simply move this to the end of vector A. And then this, the resultants from the beginning of A to the end of the entire thing, gives us the sum of the two vectors. Now to subtract, just add the negative of the second. So subtracting B from A is the same thing as saying A plus minus B in brackets. Now minus B is a vector that has the same magnitude as B, but in the opposite direction. Now, because it's opposite direction, instead of putting it like this, as we did for this one, we'll put it this way. It will be the same length, but this way. And then this will be our resultant vector. This will be our A minus B. So in this case, because we are going in the other direction, instead of adding the coordinates like we did here, because this is A plus B, we added the corresponding coordinates, x coordinate of A, x coordinate of B, we add them and so on. This time, because we are subtracting, we are going to subtract the coordinates. So A minus B will be A1 minus B1, A2 minus B2, and A3 minus B3. Now for scalar multiplication, you can multiply a vector by a scalar. That is the same thing as multiplying a vector by just a normal number, a number that is just magnitude. Multiplying a vector by scalar is the same as multiplying each component of the vector by that same scalar. So lambda A is equal to lambda A1, lambda A2, lambda A3. Now the modulus of this new vector that we get when we perform this scalar multiplication is equal to the modulus of lambda times the modulus of A. So it's just the magnitude of that scalar times the length of the A vector. Because if you remember, the magnitude of a vector is just the length of the line segments representing it. So if this is magnitude 3, and we multiplied this vector by a scalar, maybe 5, the magnitude of the new scalar will be 5 times 3, which is 15. Now, if lambda is greater than 0, lambda A is a vector with we've already seen that magnitude lambda times bigger than A, just like we did 5 times 3, 15, and it will be in the same direction as A. If lambda is equal to 0, lambda A is equal to 0 because this is just 0 times this. If lambda is less than 0, here we'll be multiplying each component by a negative number. So that will give us minus lambda, multiplying each component by a negative number. So that will give us a new vector that is going to be in a direction opposite that of A, because it's minus. Remember what we discussed here? When you have minus, we just go in the opposite direction. So if lambda happens to be a negative number, the magnitude of the new vector will still be lambda times magnitude of A, but the direction will be the opposite direction to A. Now we look at a unit vector. What is a unit vector? A unit vector is a vector whose magnitude is 1, or we say a vector whose length is 1. In some textbooks, you may see unity instead of 1. It's the same thing. Now, the length is 1, but the direction, we're not told anything about direction. So it means that there are many unit vectors. Each direction has its own unit vector. As long as the vector, the magnitude of the vector is 1, it is a unit vector. So it can be in any direction. Now, a unit vector in the direction of any vector A is written like this. Now, unit vector in direction of A is equal to A divided by the magnitude of A. Now, because A is A1, A2, A3, this is the same as dividing each component by that magnitude. So we have A1 over magnitude of A, A2 over magnitude of A, A3 over magnitude of A. Now, if our vector A is in the x direction, the unit vector in the x direction is written as I. Unit vector in the y direction is written as j. Unit vector in the z direction is written as k. Now, because this A1 is the x coordinate, is in the x direction. This A2 is the y coordinate, is in the y direction. Same thing goes for A3, is in the z direction. These unit vectors, this is in the x direction, this is in the y direction, this is in the z direction. It means that this vector A can be written as A1i plus A2j plus A3k. This A1i will be the component of the vector A in the x direction, because it is unit vector in the x direction. That is a vector whose length is 1 in the x direction times A1. And we've seen from our scalar multiplication when you do this, it is in that same direction. And then the magnitude is A1 times the magnitude of this. And remember, magnitude of this is 1, since it's a unit vector. So this part here is a vector of magnitude A1 in the x direction. This is a vector of magnitude A2 in the y direction. This is a vector of magnitude A3 in the z direction. Now, when you add up these three vectors, it's going to give you A. Because if you move in the x, and then move in the y, and then move in the z, and you add up those three vectors, just like we did for vector addition with line segments, when you put the beginning of one at the end of the other, it's going to add up to the A vector. So another way of writing this A vector is this. You have A1i plus A2j plus A3k. So now, going over all the things we've done before, we are going to express them using this new notation that we've introduced, because this notation is actually more common. Is the notation that is usually used in vectors. So A plus B, before we had A1 plus B1, A2 plus B2, A3 plus B3. Now, because this is in the x direction, it's going to be A1 plus B1 I. So this whole thing times I. Remember, I is unit vector in the x direction. This is in the y direction. So it will be this whole thing times j. Same thing goes here. A3 plus B3 times k. Now, for subtraction, it's still going to be the same method. It will be A1 minus B1 times I. It's plus A2 minus B2 times j plus A3 minus B3 times k. So this is the same as this. This is the same as this. Now, for scalar multiplication, before what we had was lambda A1, lambda A2, lambda A3. Now we have lambda A1I because this is in the x direction. So lambda A1I, this is in the y direction. So plus lambda A2j plus lambda A3k. Then for unit vectors, it's just what we've been doing all along. This part that's in the x direction will take I. This part in the y direction will take j. This part in the z direction will take k. And then you just add them up. And because this is common, we can decide to factor it out. And in that case, we'll have A1I plus A2j plus A3k all over magnitude of A. Now, we move on to section formula. Section formula is, it gives us, when we want to divide the difference between two vectors in a certain ratio, section formula gives us another vector that divides them in that ratio. So if we have two vectors A and B, this vector now is B minus A. This one here, in this, the PQ in this direction is B minus A. And if we want to divide the B minus A in the ratio of m is to n, so that this part PR will be equal to m, and this part RQ is equal to n, you simply use the section formula. It says that MB plus NA all over m plus n will give us R. And that R is the vector that divides B minus A in that specified ratio. Now, a special case when m is to n is 1:1. If this ratio is 1:1, it means that we are dividing that difference, B minus A, into two equal parts. And when you want to divide something into two equal parts, you take the average, right? So in the special case where m is to n is equal to 1:1, the vector R that divides B minus A in that ratio is just A plus B all over 2. I will move on to multiplication on vectors. Now, there are two ways of multiplying two vectors together. We have the scalar product or the dot product, and we have the vector product, also known as the cross product. Now, the dot product is written as A dot B, and the formula for it is modulus of A times, modulus means magnitude. So magnitude of A times magnitude of B times cos theta, where theta is the angle between the two vectors. Now, in most questions, you won't really be given this angle. In fact, they may even tell you to solve for the angle. What you'll be given is just A and B. but you'll be giving them in terms of their components. You'll be giving them as A1I plus A2J plus A3K, B1I plus B2J plus B3K. Now, if you have just the components, you can use this formula to find the dot product. A1B1 plus A2B2 plus A3B3. So you just multiply the components that are in the same direction. For A1 is in the X direction. For B1 is in the X direction. We multiply both of them together. Then we have A2 and B2 are in the Y direction. We multiply both of them. Same thing goes for the third one. A3 and B3 are in the Z direction. We multiply both of them. Now note that we don't add that I, J, and K because this dot product gives us a scalar quantity. The dot product of two vectors gives us a scalar quantity. So we're not going to be having I, J, and K because this is no more a vector. Now, to find cos theta, assuming we're asked to find the angle between the two vectors, we can still use this formula. Just at this time, instead of using this form to find A dot B, we use this components form. So here, we'll just write A1 plus B1 plus A1B1, plus A2B2 plus A3B3. And then if we divide both sides by the product of the magnitudes of the two vectors, we have a formula for cos theta. So cos theta is equal to A1B1 plus A2B2 plus A3B3 divided by A and B. And then to find theta, we just take the cos inverse of this whole thing. Now, I've already said that dot product gives a scalar quantity. Dot product is actually the magnitude of the component of A in the direction of B. I say that the dot product of A and B gives a scalar quantity. This quantity is the magnitude of the component of A in the direction of B. So if I have two vectors, A and B, and I find, just like we usually do, we can find the component of A in the X direction, in the Y direction, in the Z direction. We can also find the component of A in any direction. It must not actually be just A, just X, Y, or Z. We can find it in the direction of B. Now, if I know that component, if I now find its magnitude, what I've gotten is the dot product. So dot product helps us to find that. Now, the cross product of two vectors, the cross product of A and B, is written either like this or like this. Although this form is more common, so I'll be using it throughout. So A cross B is equal to magnitude of A times magnitude of B times sine of the angle between them times a unit vector n. We're going to be talking about this unit vector soon. So theta, I've already said, is the angle between the two vectors A and B. This unit vector n is the unit vector in a direction perpendicular to both A and B. So if I have two vectors A and B in a direction perpendicular to both of them, the unit vector in that direction is what we mean by this. Now, just like before, most times you won't be given this theta, and you also won't be given this. So how do you find the cross product? It can also be written in terms of its components. This is a formula for cross product. A cross B, A cross B is equal to A2B3 minus A3B2 times I plus A3B1 minus A1B3 times J plus A1B2 minus A2B1 times K. Now this is quite long, it's sometimes hard to memorize. So another way of writing this cross product is using a matrix. It can be written as the determinant of a matrix, a 3x3 matrix. The first row is I, J, and K. The second row is the components of A, that is A1, A2, A3. And the third row is the components of B, B1, B2, B3. So this is what we have here. So finding the determinant of this matrix will give us the cross product of A and B. So if you remember how to find determinants, it will be this times determinant of this smaller matrix minus this times determinant of these two together plus this times determinant of these two together. Now to find determinant of this smaller one, we'll simply do this times this minus this times this. So A2B3 minus A3B2I minus A1B3 minus A3B1J plus A1B2 minus A2B1K. Now this minus, if we put it into the brackets, these will change signs. So minus A3B1 becomes plus A3B1. This becomes minus A1B3. And this is a formula for cross products, just like we had here.